but this sunspot group is very, very active, grew tremendously while it was on the far side. We see that activity right here as it rotates towards the eastern limb solar coordinate system, and that is a sort of electrical and plasma crackling and bustling activity that you usually see before high M class or even X class solar flares. So this sunspot group has already been very active over the past few days. We have our coronagraph imagery, which shows all those coronal mass ejections launching off to the left. That's again to the east solar coordinate system. Now it's going to be rotating to view. So we can expect radio blackouts on the sunlit side of the Earth anytime there's a big solar explosion from that sunspot group or another. And then if it launches coronal mass ejections our way, that could impact us if it's really quick in about 24, maybe even less hours than that, but typically 2 to 3 days. It depends on that velocity. And when you get that impact is when you get a geomagnetic storm. Earth's magnetic field undergoes these big swings in field strength, and you have these powerful electric currents that are generated all across the Earth energy onion, as I call it.
The eruption of solar flare AR430 on December 4th was classified as an M-class event. Not the most powerful, but strong enough to disrupt satellites, GPS systems, and cause minor geomagnetic storms. Earth's space weather models predicted the flare would brush against the planet's magnetosphere within 14 hours. Agencies issued routine alerts. Power grid operators were advised. But what happened instead was anything but routine. Roughly 5 hours after launch, Stereo A and B, alongside Japan's Hisaki Observatory, detected something strange. The flare's plasma stream, usually a wide, diffuse band of charged particles, began to narrow. It was no longer moving toward Earth. Instead, the energy stream veered subtly, bending in space. This was not atmospheric drag, it was not solar wind redirection. The flare appeared to be adjusting course. Incredibly, its new trajectory intersected perfectly with the corridor of 3I Atlas, an interstellar object already known for breaking the rules of celestial mechanics. Within hours, ground-based observatories confirmed the impossible. The solar flare never arrived on Earth because it had been intercepted mid-space. When the flare made contact with Atlas, scientists expected a visual storm, flaring, outgassing, tail formation at the very least, but there was nothing. The object absorbed the energy silently, then pulsed once with light, and the flare vanished. This was not a glancing interaction. The flare should have continued past the object and dispersed, but every measurable portion of the stream ended at the coordinates of Atlas. It wasn't deflected, it was stopped. This is the first time in modern space observation that a comet-like object has taken the full brunt of a solar plasma stream and showed no instability, no chemical reaction, no orbital deviation, only silence. And that silence changed everything. Immediately after the flare made contact, Atlas emitted a short pulse of visible light, but it wasn't explosive. It didn't resemble the violent flare-ups seen when ice-rich comets react to solar impact. There was no chaotic plume, no debris, no vaporized surface ejector. Instead, what occurred looked eerily deliberate. The flash lasted exactly 2.9 seconds, not a moment longer. It began as a smooth increase in brightness, rising evenly across the entire visible surface of the object. No hotspots, no trailing edges, just one unified glow, like a flashbulb in the void. Then it faded just as cleanly. The timing was critical. It occurred after the flare was absorbed, not during, not before, almost as if the object was responding, not recoiling, but reacting. Telescopes tuned for ultraviolet and infrared picked up nothing. No heat bloom, no spectral signature of chemicals like water vapor, cyanogen, or carbon monoxide, all typical in post-flare sublimation. Even metallic asteroids exhibit minor heat shimmer when struck by solar radiation. But here, there, was silence. What makes this so puzzling is the uniformity of the event. Natural surfaces, even polished rock or ice, reflect inconsistently due to shape and texture. But Atlas's flash was distributed with machine-like symmetry. Some compared it to electrical capacitors. When charged material reaches a discharge threshold, releases energy, and then stabilizes. Others noted similarities with engineered plasma containment systems, where controlled light output is used as a form of stress response. Either way, the light wasn't accidental. It wasn't fire, it was acknowledgement. And when the flash ended, the object returned to normal. No brighter, no darker, no thermal residue. It was as if the flare had never happened at all. Every natural comet exposed to solar wind behaves predictably. It forms a tail. Gases and dust erupt from its surface as volatile materials sublimate, leaving a distinct coma and light-scattering trail. But when 3I Atlas was hit by a solar flare strong enough to rip ice off a mountain, nothing emerged. No tail, no coma, no gas. Astronomers waited, they tracked, they recalibrated instruments to ensure no emission was missed. Ground-based telescopes in Hawaii, Chile and the Canary Islands focused on the object for hours. Still nothing. This wasn't subtle behaviour, it was complete inertness. The surface of Atlas didn't scatter sunlight. It didn't develop a faint haze of particles. Even at high magnification and long exposures, there was no halo, just a sharply defined point of light, as if the object was solid, cold, and entirely immune to solar radiation. Even metallic objects in space exhibit some form of reaction to plasma exposure. They heat, they reflect, they distort. But this wasn't reflective shimmer, it was stillness. Spectral scans revealed no traces of cyanogen, no ammonia vapour, no ionized particles that should have been excited by the flare. Nothing to suggest movement, erosion, or evaporation. Just flat lines. That absence of data was the data. If the object is truly solid, it would need to be made of something far denser than rock, perhaps a form of carbon compound unknown to current science. But even that doesn't explain the total absence of energy dispersal. It didn't just fail to react, it rejected the flare as if the energy had nowhere to go, and so it simply stayed where it landed. Roughly 6 minutes after the solar flare contact, several telescopes reported a second anomaly, a soft glow forming around Atlas, visible only in polarized light. It lasted just under 90 seconds, a symmetric envelope of luminosity, almost like a bubble. But this wasn't a tail, it wasn't particles, it was structure. The glow surrounded the object evenly, showing no signs of turbulence or material flow. In spectropolarimetric analysis, the shell radiated evenly, not in random scatter, but in a narrow controlled band. This indicated energy, not matter, was being released. Think of it like a magnetic containment field. That's what some scientists began calling it, a temporary magnetic skin. That term isn't just poetic. It suggests the object absorbed the flare's energy, and instead of ejecting it, redistributed it across its surface. This behavior mirrors how spacecraft manage thermal loads using radiative panels, smoothing out spikes, then dispersing them without mechanical disruption. But Atlas has no visible panels, no surface components, no known materials, so how is it doing this? Theories began to emerge, from superconductive outer layers to embedded electromagnetic damping systems. But these ideas all assume one thing, that Atlas has internal structure. And structure implies design. Nothing in the solar system exhibits this kind of temporary energy buffering. Not asteroids, not moons, not even artificial satellites, unless they were built for this purpose. Whatever that flare did to Atlas, it wasn't damage, it was processed. And when the shell faded, everything went back to baseline. No particles, no fragments, just silence. Again. Energy leaves fingerprints. Every action in space, no matter how small, has consequences. When a body is hit by a mass of solar plasma, it should react. A shift in course, a wobble. Even the slightest nudge can be detected using current orbital tracking systems. But when 3I Atlas absorbed the flare, it didn't move, not a millimeter. Global observatories confirmed this independently. From NASA's Deep Space Network to radio observatories in France, Australia and Japan, every set of orbital predictions matched. The object's velocity and trajectory were exactly the same before and after the flare. There was no drift, no acceleration, no deceleration. It stayed on path with surgical precision. This shouldn't be possible, not for an object several kilometers wide. Even small comets, when struck by solar radiation, exhibit tiny velocity shifts caused by asymmetric heating or outgassing. Those shifts add up, often requiring recalibration of trajectory models. But Atlas maintained perfect orbital fidelity. There are only two plausible explanations for this. Either Atlas is made of an extremely dense, symmetrical material, so perfectly balanced that even a solar flare cannot push it, or it's compensating. Compensating means active control, the ability to absorb external force and negate its effect. Only engineered systems can do that. Satellites, spacecraft, precision probes, these are built to maintain orientation and course despite collisions or energy surges. Natural objects react. They don't neutralize. So if Atlas didn't move, we must ask, is this due to structure or strategy? And if it's the latter, then someone made sure it could. Reflectivity is one of the most basic metrics in observational astronomy. When sunlight hits an object, how it bounces back tells us a great deal about that object's surface, its shape, texture, composition, and spin. But Atlas just introduced a new category, the unnatural spike. Following the solar flare contact, the object's surface exhibited a sudden, measurable increase in reflectivity. But it wasn't chaotic. The brightness increase was smooth, uniform, and lasted precisely 2.4 seconds. Then it returned to baseline. What's more confusing is what didn't change. There was no detected change in spin rate, no angular drift, no surface wobble. All the expected indicators of momentum exchange were missing. The flash occurred, and the object held position with alarming stability. Normally, reflectivity changes result from physical movement, either spinning debris, freshly exposed surface patches, or vapor plumes catching sunlight. Here, none of that happened. The increase wasn't directional either, it was spherical. A brief, even glow around the entire object. It's as if Atlas chose to flash. Some scientists now suggest the event was not reflective at all, but emissive, that it radiated stored energy rather than bouncing sunlight. If true, that would explain the lack of physical consequence. But it raises another question. What kind of material stores solar energy and emits it back in precise timed bursts? There are no known natural analogues. Only engineered reflectors or composite plasma shells behave this way. Whatever caused the reflectivity spike, it didn't result from the solar flare randomly hitting a passive surface. It felt regulated.